Hello and welcome to another video in this series as we learn the basics of Lean to write simple maths proofs. Today we're going to be using the lemma we wrote last time. So in the last video we created our own lemma, and yes, we provided a small minimal example of how to use it, but today we're going to be attacking a slightly more chunky maths problem. Not very difficult, but slightly more interesting, I guess, with our own lemma, just to illustrate using our own lemma and practicing writing Lean proofs. So today's a little bit about practice as well. So let's dive in. The task is stated quite simply, actually. For any natural number n, show that n squared can't be 7. Now, if that's obvious, great. You might sort of say, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and then all the bigger ones are going to be bigger. But none of them really hit 7. So let's think about a proof strategy. So if I've got the natural number line, sequence really, isn't it? Not line. 0, 1, 2, 3, 4. If I square this 0, square this 1, square this 4, 9, 16, and we want to prove it's not 7. So not 7, which would be somewhere here. So all the small ones end up as, when squared, end up as 0, 1, 4, so less than 7, and the ones after that, the bigger numbers I guess, all end up being 9, 16, 25, 36, bigger than 7. So intuitively we can say, well, if we split all the natural numbers into 2 so that the two sets together are all the natural numbers, none missing. If we can show that one set always ends up being smaller than 7 and the other set always ends up being more than 7, and there's no other option, every number is either in this set or in this set, so every choice leads to n squared being less than 7, n squared less than 7, or n squared more than 7. That means n squared can never be 7. These are the only two options, less than or more than, but never equal. So that's the idea, that's the kind of intuitive approach. So that's kind of the approach we'll take. It's quite a nice idea actually, this kind of splitting the natural numbers into two sets which together are the full set of natural numbers, and then showing that all the possibilities miss 7. So let's do that. So we just talked. The slides are all online if you want to have a read in slower kind of time, and the blog is also online as well. And I'd use more carefully chosen words in the blog so that you can read it. Whereas here I'm just talking off the top of my head, I guess. So the proof strategy was to split the natural number sequence into 2 and show that all the numbers small in the smaller set, or the set of smaller numbers, result in n squared less than 7, and then all the other ones n squared more than 7. And because of the only two possibilities, then n squared can't be 7. So every possible choice for n is either in one set or the other set, and it leads to either n squared less than 7 or n squared more than 7. So therefore n squared is not 7. You can see there's a lemma here somewhere that we're going to have to use. We will. See, you notice this, isn't it? This thing that where intuitively in our heads some of these things are true, or these logical leaps are true, and we've never really thought about explaining them. But when you're writing Lean proofs, you do. I suspect when you're writing pen and paper math proofs, you probably don't. But in Lean, you have to justify why this means this. So we will do that. So let's have a go at writing this out in small steps As you know, these are quite laborious, but they're important for us to break a problem down into small steps that kind of match what we would write in Lean. So they're almost like a preparatory step. So we've got a proof objective, n squared is not 7. We have our lemma, which splits the number sequence, the natural numbers, into 2. And if we use m is 2 with our lemma, we have an expression which says n is less than or equal to 2, or 3 is less than or equal to n. So we split the number sequence into a set of small natural numbers which will contain 0, 1 and 2, and then the other one will contain 3, 4, 5, 6 and all the other ones. So this is then a proof by cases, because this covers all possible eventualities for choosing a natural number. It's either the natural number is either in this set or in this set. So let's look at them case by case. In the case of n is less than or equal to 2, the smaller numbers, we have n squared is less than or equal to 4 because of this. Because n is less than or equal to 2, so n squared is less than or equal to 4, which is less than 7. So n squared is not 7. So we have to justify why less than 7 means it's not 7. Again, it sounds incredibly super obvious, but we have to justify every step in Lean. So there is a little lemma, a mini tiny lemma, that says a is less than b implies a is not b. It's almost a statement of obvious. But there you go. We're going to have to make use of that. And then in the other case, for the larger numbers, n squared is more than 9, because n is more than or equal to 3. So that's more than or equal to 9, which is more than 7. And then by using another tiny, minuscule lemma, that's not 7. So that teeny lemma will be a is more than b, implies a is not b. Again, it sounds like statements of the obvious, but we will have to make use of that just to cover that gap in the logic. So both of these things, both cases lead to n squared is not 7. And that's the conclusion we wanted to prove. So yes, this is a little bit laborious and long-winded, but it takes us halfway there to a Lean proof. So this is talking through what we've just talked through, so you can read that in your own time. Should we live code this or not? Yeah, let's live code it. So I'm going to be using the online environment. You can install Lean yourself, or you can use the Visual Studio Code with the Lean extension, which creates a nice environment actually. But if you don't have Lean installed, you can just use the online version, which doesn't require anything to be installed. So what are we looking at here? This is what we developed last time. This is a lemma that splits the natural numbers into 2 that we developed last time. So we've just copied and pasted it here. And because it says a lemma then a name rather than example, let's see, if I said example, that would still be valid as a proof, because that's what most of the examples we've been looking at. So there's no the server stop. If the server stops, you can just reload the page and it should start again. I think it times out. So yeah, we've given it a name so we can use it later. Right, so we want to prove n squared is not 7. And we said the proof strategy is to split the natural numbers into 2 using our lemma. So let's try that. Let's create an intermediate result. Let's call it h, which says that, well, where did we split it? Let's look at our maths proof again. We split it from 2 and then 3, didn't we? So we are going to say a or n is less than or equal to 2, or 3 is less than or equal to n, justified by our lemma, which is nat add 1 le. Oh no, that's copying the wrong one. Nat le or successor le. Now that's giving me a warning, because I haven't provided those two parameters, which are mandatory because of those round brackets. So what are those two? Which way around were they going to be? So we want A to be n and B to be 2. There we go. So that will give us a hypothesis that says n is less than or equal to 2 or 3 is less than or equal to n. So we've split the natural numbers into two, that set and that set. So we've made use of our lemma to do that. Great. And then that's a proof by cases. So we have two cases. Obtain, as usual now, HAHB. Give them a name that you want, but choose something that makes sense. Split that. That gives us our two cases, which are n is less than or equal to 2 or n or 3 is less than or equal to n. So focusing dots, always a good idea. So our temporary current goal, our proof goal is n squared is not 7. So if I apply that tiny lemma, so apply, what was it? We need to look it up, don't we? So I think it's going to be called not equal from of less than. Let's find that. Oh yeah, there it is. So it says that if A is less than B, then A does not equal B. If we apply that to our current goal, then all we have to prove is this. And then we've got this. So apply any of LT. Okay, so that has changed our proof objective to n squared is less than 7. If we actually looked at this idea way back in an earlier video where we introduced the application of lemmas, but let me just draw a picture just to kind of explain what we've done there. So we wanted to prove n squared does not equal 7. If we have a lemma that says A is less than B implies A doesn't equal B, then we can see that the right hand side of that lemma matches our goal. So if we can prove this, then that's equivalent, that implies A is not B, which is that. So if we can prove n squared is less than 7, by this lemma we've proved n squared does not equal 7. We've done this before, so do go back if that's unfamiliar. That's what we've done by applying that lemma to this proof goal. We've changed the goal from this to this, which is that one. So how do we prove that n squared is less than 7? Well, we can do a calc section. So we can say n squared equals, and now we've got the case, we know that's the case, this is the n is less than or equal to 2 case, so that's LE 2 squared, which is 4, and we have to justify that by rel HA, and it wants it to be of the same pattern, so there you go, n squared is, you'll find that sometimes, so that's n squared is less than or equal to 2 squared, which is 4 by arithmetic, norm num, which we know is less than 7 by norm num as well. Was it num norm? I've got to put by. There you go. Now we can probably compress this into 1. So 2 squared is 4, and that, if I remove that, that should be fine. So we can shorten the code without reducing the clarity. We can see that's 4 and that's less than 7. So that's proven the first case, and then the second case will be very similar. And instead of proving, we want to prove n squared is not 7, but this time we want to prove that all the n squareds are bigger. So we want to apply not equal of greater than, which is, if looking at that, if B is less than A, then A is not B. So let's apply that and see what we get. 7 is less than n squared. Yep, that's what we want to show. We do that with a calc. N squared is greater than or equal to 3 squared by rel hb is the second case, and then we can say that's more than 7 by norm num. Does that work? It does. No errors or warnings. Lovely. So that was a more interesting proof, using more interesting kind of proof strategy, but it was a chance to practice using our lemma. So it was crucial for us to use our lemma to split the natural numbers into 2 sets. So that's what we've done there. Just to add again, this lemma that we've written doesn't exist in Mathlib, probably because there's a very similar one. But I find this one more convenient. As I said last time, it's kind of symmetrical. It uses less than and less than, whereas the one in Mathlib has less than or equal there, but then less than, so it's a little bit different. So I find this one to be just sits nicer in my brain. So I hope that was interesting, a chance to use our own lemma. Now you might be thinking, well, if we're going to be using the lemmas we write again and again, you don't want to copy and paste them, and that's true for 2 reasons. If you copy and paste them into every proof, then you lose track of them, and if you need to update them or fix them, then you have to find wherever they got to. So it's better to have them in one place in a library and then refer to them from there. So let me draw a picture to explain that point. So if we write a lemma and then we have several proofs, whoops. So if we have a lemma and then we have several proofs and we copy and paste at the beginning of each one, if we wanted to change this, we'd have to go and find wherever it was used, and we might not be able to do that. It might be other people using our lemma, so that's bad. That's really bad, in fact. So a better idea is to write our lemma and package it up in a library so that other proofs, whether they were ours or other people's, just make a reference to the import our library in the same way that we import Mathlib libraries. So they use our lemma after importing our library, and if we improve or fix an error or update it, then they automatically get the benefit without us having to go and chase. So putting lemmas into libraries is something you might want to think about doing if your lemmas are going to be used more than a few times. Now that isn't the central purpose of this course. The central purpose of this course is about a little bit of mathematics and how to use Lean to do that mathematics. So this software engineering of libraries isn't really what we want to do. But if you look at the website, the blog, there it is, and if you look at the contents, scroll down, there is an appendix which talks about how to do that. Now there are better, more sophisticated ways, but what I've presented is a very simple way for creating, putting your lemmas and theorems and definitions, actually, as we'll see later, into libraries. If you get more sophisticated, you can follow the official kind of approach. It just requires a bit more work, but this is good enough. So briefly, your project folder will have a file called lakefile.lean, kind of like a makefile, I guess, if you know what that is. And then we have in there leanlib, and then the name of your file, your lean file that contains your lemmas. I've called this one my lean lemmas. Yours will be a different name. So by doing this in the lakefile.lean, it tells Lean that there is this library, that exists, and makes it available. then other lean programs can simply import mylean lemmas, or whatever you call it, and then make use of your lemmas by name. So it's as simple as that. So that's a simple approach if you want to do that. Great, so I think we've covered everything we wanted to do today. The task, the exercise at the end, call it easy exercise, not to be patronizing or kind of anything. The idea is that we don't choose difficult maths or torturous maths. The idea is to keep the maths simple and just practice the lean. And often you can do that by just mirroring and adapting the example we've given. So here the idea is to write a lean proof to show that n cubed does not equal 10 for any natural number n. So let's talk through how we might do that. So we've got the natural numbers 0, 1, 2, 3, 4, and we want to show that n cubed does not equal 10. And let's have a look where these go. If I cube that, I get 0, cube that, I get 1, cube that, I get 2 times 2, 4 times 2, 8, 3 times 3, 9 times 3, 27, 4 times 4, 16, 32, 64, and so on. So these get bigger and bigger. And you can see that if we do a split there, then all the smaller natural numbers are less than 10, and then all the bigger ones are more than 10. So similar idea. So if we can show that n cubed is less than 10 or more than 10, we've shown that it doesn't equal 10. So that's the same idea. So you should be able to mirror the proof that we've done and adjust it a little bit to do that. So have fun doing that. Any problems, do comment and we'll have a discussion. See you next time. Bye.